Okay, so I have had a chance to go through and read hundreds of questions and replies from everyone up until this point. Before we proceed to the next lesson, there are some clarifications I need to make from the previous lessons. Some of these involve possible misunderstandings that may have come about from the way that I explained a particular topic, and others involve common questions that have been coming up in the various comment threads. So first of all, let's talk about include statements. In the lesson on include statements, I explained that you use include statements to, in effect, copy and paste the contents of some programming source code into your existing program where you put the include statement. With C and some other languages, this is technically correct. It does not, however, address the real purpose. It is extremely bad programming practice to do things this way. You do not put code in a file and just cut and paste that code using an include statement to where you want it. What you are really saying with an include statement is that you want to use the contents of the included file within your program. In other words, the include file contains code, especially functions, that will provide useful functions for your program. So take a look at this line of code. Think of this as meaning I plan to use functions that are found in this file, stdio.h, in my program. So again, don't think of it so much as you're cut and pasting the contents of stdio.h into your program. Think of it as you're saying you want to use the functions that are contained in stdio.h in your program. Although, in this case, technically what you are doing is you are basically taking the entire contents of the file and, in effect, putting them right here in your program, but I want you to understand what the purpose of that is. Okay, so now let's talk about the basics of numeric overflow. When we speak about numeric overflow, we are referring to any time any mathematical operation produces a result which cannot fit in the number of bits we allocated. For example, if we have 4 bits and we perform a mathematical operation that results in the number, let's say 25, that result will not fit in our 4 bits, and therefore we have a numeric overflow. While there are similarities, this is not the same thing as a buffer overflow or a stack overflow, which will be the subject of at least one future lesson. So, numeric overflow refers specifically to a situation where we have a number that is too large to fit in the space that we've allocated for that number. Now, about the basics of fractional numbers in binary. I have explained in a previous lesson that the radix point is the term used for the equivalent of a decimal point in binary. And for example, if we have, this is effectively the same thing as 2.5 in decimal, because what we're saying here is 2, then we have the radix point, and then this is effectively 1/2. We went over that in the fractional binary number lesson. Now I need to be extra clear on 3 points. Let's okay, still too long and still too long. Okay, so the first point is the radix point is not actually encoded in binary. So let me just put that number back up. Okay. Rather, it is understood by knowing how many bits correspond to the part of the number to the left of the radix point and how many bits correspond to the part of the number to the right of the radix point. You do not actually encode the radix point itself in binary. Second is that the part of the number to the left of the radix point is known as the integer part, and the part of the number to the right of the radix point is known as the fractional part. Okay. Now, we had a lesson on the basics of numeric data types in C. I have not yet covered all numeric data types. And in that lesson, or up until now in general, there are still some numeric data types that you haven't yet learned about. So I want to make sure that you understand that. We will be learning about those as time goes on. Also, as has been pointed out, the term long double has nothing to do with combining a long value with a double value. It is actually often 10 bytes in size, although it may be stored in 12 bytes, and this depends on various factors that are beyond the scope of this lesson. But I just want to make sure that you understand that when you write long double, you are not combining a long value with a double value. If that's confusing to you, don't worry about it too much. This is just a technical clarification that I need to make in order to make sure that these lessons are technically accurate. Similarly, the sizes of a data type, such as unsigned short int, being 2 bytes long, differs from compiler to compiler. So in various lessons where I have said unsigned short int, and I've talked about an unsigned short int being 2 bytes in size, that may or may not be true. It depends on the compiler, and we will be getting more into that later. But I don't want you to be writing programs where every time you see unsigned short int you think, oh, 2 bytes. Not necessarily, but we will get into that more later. These clarifications are especially important if you plan to write code that will be open source, or you are planning to make the source code generally available. In those cases, you must be mindful that if you are using a data type of a specific size that works on your computer, it may not be the same for someone else who compiles that same source code. If they use a different compiler, they could have a data type size that is different than yours. You might have an unsigned short int that is 2 bytes, they might not, and then suddenly when they try to take your source code and make a working program, they won't be able to. So for that reason, it is very important that you write code that is designed to work on any compiler that follows the particular standards that you have in mind. For example, ANSI C, and we'll get into that more later also. Okay, so the next topic is about the character data type and the basics of ASCII. Here, and in general, I showed you the following rules concerning how text and numbers are encoded in binary. I said that if a byte begins with 010, that it's going to be a capital letter. All capital letters start with this. 011, all lowercase letters start with this. And 0011, all numbers as encoded in text start with this. For example, the number 1 would be like so. Keep in mind that this is not reversible. This means that you cannot say that anything which starts with 010 is a capital letter. There are many characters that are not numbers or letters. For example, braces, parentheses, so on. And many characters that start with 010 may not be a letter or a number, and so you need to be aware of that. While it is true that all capital letters do start with this, not all characters that start with this are capital letters. So you should be mindful of that fact. Okay, next topic. Regarding variables. So in that lesson I showed you how to create a variable. For example, like so. The question was raised, what if you don't specify a value? What if you just write int height? This is legal. You can do this and it will create the variable. However, anything at all could be its value. Why? Because when C creates the variable height, it only decides where in memory that variable will reside. It does not set a value for it. So looking at our 16-byte RAM example briefly, let's suppose that before you write this code, this is the state of RAM. I'm just going to come up with a series of random ones and zeros, and you write int height, just like that. What's going to happen is C is going to look at this variable and say, okay, I need to find somewhere in memory for it, and it'll decide, let's say, this position in RAM. That's it. It's not going to change what's there. It's only going to decide on a memory address. When you write int height equals 0, on the other hand, it's going to decide on a memory address, locate that memory address, and then set everything to 0. It is important that you understand that as a programmer you should always initialize a variable when you create it to some value. Usually 0, but it can be whatever you want. Common practice is to assign a 0 to a variable until it has been used. And the reason you do that is because that way you don't have unexpected situations come up where, because the value was something you didn't expect and you forgot to initialize it later on in your code, you come up with some unexpected behavior. So you should always initialize a variable when you create it. So instead of writing this, you should write this. That way you don't have any problems later on in your program because of whatever that value happened to be set with. Okay, so next topic, about terminating strings of text and other data. So there are consequences of not terminating a string of text or other data properly. Earlier I explained that if you have a string of text that is not terminated, that does not end in a termination character, the program could just print garbage by basically locating a position in memory, printing what's there, going to the next byte, printing what's there until it gets to the end. Also, however, the program could simply crash, because as the function, like for example printf, cycles through memory looking for a byte that happens to have a 0 value, it might encounter memory that doesn't belong to your program. The operating system generally doesn't like it very much when your program tries to work with memory that doesn't belong to your program, and the operating system will usually crash that program. Now technically the behavior is undefined, which means anything at all could happen. It is a common joke on gamedev.net to refer to accidental firing of nuclear missiles as a result. Your computer is almost certainly not going to fire a nuclear missile, but it gets the point across. Undefined behavior means anything at all could happen. So Keep in mind that you must terminate strings of text and other data properly, because if you don't, anything at all could happen, which can create a bug that is so difficult to track down that you'll be spending hours trying to figure out what went wrong. Okay, so next topic, assigning a value to a pointer. One thing that I did not cover during that lesson, and therefore some people may have missed, is this. C is very forgiving when it comes to spaces. For example, if I write these two lines of code, notice that I have a lot of spaces here, I have spaces here, or maybe here. Both of these lines of code are the same. They're both valid, and they're both going to work just as well. Now, good programming practice is to format your code so that it is easily readable. For example, you would never do this, because then it is hard to see that you're missing it makes it look like you're missing a semicolon, and it would be very easy for someone to look at this code and say, oh, it's missing a semicolon, and that isn't what you want, because it could lead to someone thinking there's a bug when there isn't one. So you want to format your code in a nice, easy to read manner, and we'll get into some of the details of that later. But I want you to understand that as far as C is concerned, how you put spaces really is up to you. Any of these lines of code are perfectly valid. Okay, next topic. About pointers concerning multi-byte variables. So in that lesson, I showed you this code. Then I explained, as is logically apparent from reading this code, that this has the effect of first changing height to 8 and then changing width to 4. This would be correct if height and width reside in memory one right after the other. This is one of the assumptions being made about our 16-byte RAM that I've used in these types of lessons. Do not ever write code like this in a real program. Your compiler chooses where to put variables you create, and you have no way to know if they will be stored in RAM the way that this example assumes they are. This code is for instructive purposes only, to show you how pointers work in general. Now, some clarifications about the printf function. It has not been addressed directly in a lesson, and even though you have likely seen it used, with the printf function, you can give it multiple parameters if you want to print various types of data. For example, this is perfectly valid. It's perfectly fine to send as many different parameters to the printf function as you want. And the output here, of course, would be height, which is 10, and width is 5. That would be the output. Now, something very important about the printf function. Up until now, every time we have used the printf function, we have done all of our printing on one line. So for example, with these two lines of code, let's just write a quick program here. Let's run this. And you see what happens. It prints hello and world on one line. So now I am going to show you how you can split text into more than one line. Now you remember that I showed you have a special character that is the null termination character, which is all zeros, and you can use this at the end of a string of text to terminate it. Now when you write a string of text, that character is invisible. You know it's there, but you can't see it. There is another character that means end line. That character, the thing about this character is you can't write it. There's no key on your keyboard that lets you create this character. So because of that, you have to use a special syntax with C that I'm about to show you. So let's suppose we want to print hello, and then we want to have a new line, and then we want world, like that. There is a character that means new line. The way you write it inside of your printf function is like this. So this is the character. It's one character. It's not two characters. This is just something that you write in order for C to understand that you want the end of line character. Now, like I told you, that is one character, which means it is 1 byte in size. So you're probably curious, what does that character actually look like? It looks like this. Or in hexadecimal, oops, it looks like that. So the character, which in binary is the value of 10 and in hexadecimal is the value of A, is what you use in order to end your line. And I'll show you how this looks now. Well, first, okay, now take a look. Now take a look. Hello world on 2 different lines, because the /n character will mean new line. So when the printf function sees this, what it's going to do is, first of all, no, the printf function is not good. Let me start over and make sure that I really explain this accurately. Okay, so when you write this line of code, you are doing 2 things. First of all, you are creating a string, constant in memory, hello world, with a /n character. That means that somewhere in memory there is a position with an H. After that, there is an E, and so on. And then there is going to be that /n character. And then, of course, W, O, and so on, all the way to the end. So, yeah, just for the sake of completeness, let me go ahead and write this out. Okay, so here you go. I just paused the video while I did that. So this is what your string of text is going to look like in memory. Now at this position where the /n is, what's going to happen is a single byte that will look like this. That byte means new line when printf reads the string. So first, that's the first thing you're going to do. You're going to be creating a string constant in memory that looks like this. Now the printf function is going to effectively get the memory address where this string begins, which is going to be here. So printf is going to look here, see the H character, and print the H to the screen. Then it's going to print E, L, L, O, and then when the printf function reaches this byte, it is going to simply print to the next line. It's going to understand that this is the end of this line, and it's going to go to the start of the next line, and then here it's going to continue printing. So what I want to make sure that you understand is that this is a special way that you tell C that what you want is this, which means the ASCII character byte that means new line. Even though we're writing 2 characters here, it's just a special way to tell C that we want this particular byte, because there's nothing on your keyboard that you can type that actually is that byte. Now, the last clarification that I need to make about the printf function is that many of you have used printf with the %p option, like this, in order to print memory addresses using pointers, which is great, and it helps to cement your understanding about pointers. But be sure that you remember this. What will be printed is the address in the pointer, not the address of the pointer. So if, for example, I have this, if I have, let's say, int height, let's say int height equals 5, int sum pointer equals the address of height, what is going to be printed with this line of code is going to be, in this case, the memory address of height. Not the memory address of some pointer, not where some pointer is located in memory, but rather what is inside this pointer, which means the memory address of height. So keep in mind that this code that I'm about to show you is invalid. Do not do this. Remember that asterisk some pointer translates to whatever is at the memory address stored in the pointer. It does not translate to the memory address of the pointer. It also does not translate to the address stored in the pointer. What it means is what is at that memory address, which in this case would be the value 10. Using asterisk some pointer in this example results in 10, which is the value stored in height. In other words, what is at the address stored in this pointer is the value of height, which is 10. So if any of these clarifications have been confusing to you, or if you have any questions, feel free to ask and I'll be glad to help you out. And that concludes this lesson.